All right, so we have had a change with sport now, but it seems like all of you are still, you were with me the last quarter. Yeah, or not last quarter, this quarter, but before the change in sport. Okay. All right, so what I want to do first is I just want to go back to what we've done in the last lesson or two. I just want to revise. You know, those of you who've had me before know what my style is. I like to waltz forward and backwards. Right, so this concept is very important, the concept of a standard solution. All right. The standard solution is a solution that has a known concentration. Okay? Standard solution is it's got a known concentration. It's something that you say, okay, I want a 0.1 mole per cubic decimeter solution of, for instance, sulfuric acid. Then for a practical. So then what you do is you actually work out how much sulfuric acid you need to actually put into a container. You have these measuring containers. Let me just get one for you. So you would, if you're doing a large quantity, this is a 2 liter, then this is called a volumetric flask, okay? So there's a line here that at 25 degrees Celsius, if the meniscus, the bottom of the meniscus is on this line, then you know you've got exactly 2 liters, give or take, plus or minus, does it give a plus or minus here? It's at 20 degrees Celsius because everything expands and contracts. So 20 degrees Celsius, you know that if you dissolve whatever your solute is into distilled water, must be pure water, then when it's fully dissolved and the meniscus is in line with this, there's a cut in the glass all the way around, you know that you have the solution's volume is 2 liters. It's called a volumetric flask. We make standard solutions in this. So when you do chemistry pracs, like at the end of the year when we do the titration practical, prior to you doing the practical, we will actually make the standard solution in here. Okay, we'll talk more about that later on. All right, so we looked at how to calculate the concentration of a standard solution. All right, if you're given the mass of 150 grams of sodium hydroxide and it's dissolved in 255 milliliters, what the concentration is. So the method is you use the number of moles of the mass over the molar mass. That will give you the number of moles. The method of concentration that we use is moles per unit volume. Right? So we can use little c. You can use little c for concentration, or you can use square bracket. Number of moles of solute over volume of solution. And the big M is a shorthand way of saying moles per cubic decimeter cubed. You can use it, you're allowed to use it. So we did that first. Then I showed you a short method where you take these two equations, this one and that one, and you substitute for N in here with mass of sample over molar mass. Right, and then what you get is that formula, which you do get on your summary, on your formula sheet. So concentration is mass over molar mass over volume of solution. It's a very, very handy formula. It's a handy formula, okay? So it combines the two formulae into one, right? And so you can very quickly, in one basic calculation, you can do two calculations. You can do the number of moles and the concentration calculation and gives you the answer. Cool. Any questions on that? Are we okay? Okay. Then we looked at dilution. So dilute implies to decrease the solution's concentration by adding a solvent. Okay? So a 300 milliliter, 5 mole per cubic decimeter cube solution of HCl needs to be diluted to 0.15 mole solution of HCl. How much water must be added? Right. So initially, you have 300 milliliters of a solution with that concentration. Working out the number of moles of the solute, you take concentration times volume, 300 moles. Now I can tell you now, ladies and gents, we're always going to give it to you in milliliters or cubic centimeters. We're not going to give it to you in liters. So you have to convert this to cubic decimeters cubed. Okay. So if you do that, 300 milliliters, you've got to divide by 1,000, because there's 1,000 milliliters in a liter, right? And so you get that the number of moles of the solute initially is 0.15 mole of HCl. Now, when you dilute, the key thing is, when you dilute, you add volume of solution. Now, you add volume of solvent, but you do not change the number of moles of solute. I'm going to say that again. The number of moles of solute in a dilution stays the same. What you're changing is the volume of the solution. So we do that by adding solvent, which is water. You can do this with other substances, but we generally work with acids and bases. We work with waters or salt. Adding H2O. Now note, look at my drawing. The same amount of solute, 0.15 moles of HCl was there, 0.15 moles of HCl is there. But now we've added extra water. Delta V. Delta means change. We have changed the volume by the amount of water we've added. Okay. So now the concentration will definitely change. It's going to be less because it's the same amount of moles of solute in a bigger volume of solution. All right. They tell us that we want to dilute it to a 0.15 mole per cubic decimeter cube solution. We want to make a standard solution by dilution. Okay, so you say, okay, well, the concentration of the final solution's concentration, okay, that concentration is going to be 0.15, which is less than the 0.5 because we dilute. We have the same amount of moles of solute, not water, not the same amount of moles of solvent, same amount of moles of solute. Okay, so sorry, it looks like my camera here is a little bit, right? We have the same amount of moles of solute. I'm just checking here that my camera looks a little bit. No, look here, sorry. That looks better. The camera looks a little bit misty. That's much better. All right. Okay, so when we work out the final volume, we see that, okay, so V final is going to equal 0.15 over the new concentration, the desired concentration. We get that the final volume must be 1 cubic decimeter cube. Now, what you need to add is the difference between the final volume, where the concentration is 0.15, and the initial volume, where the concentration is 0.5. And that gives you that you need to add an extra 0.7 cubic decimeters cubed. Now, this is exactly what we do when we prepare standard solutions of HCl and H2SO4. We take a bottle of HCl, which has got a known concentration out of the storeroom. It's got a super high concentration, and we work out exactly what we decide what concentration we want to dilute it to, and then we use this calculation and we determine how much we add in a volumetric flask. Okay. Now, there's a shortcut. And the shortcut is the dilution equation. If I can give you a little bit of advice about this section on acids and bases, and you're going to see it today when we do titrations and next week. Do not only rely on the shortcut methods, because we have an ability to structure questions that force you in such a way that you can't use the shortcuts. So there's time where you can use the shortcuts, you must be able to do the long methods. Yes.
So I would think that it's a little counteractive to the point of the shortcut, because in like real world science, you would be using that shortcut. So why discourage it?
Well, the assumption is in real world science, you've got a PhD in chemistry and you've used it so many times, you don't need to use the long method because you are a professional. But you're on school level, so we need to still get you to really understand it. And the way we do that is the way we structure the question. We scaffold it. You'll see, we do this. And the other thing is with titration. So what we don't want to do is use a shortcut without understanding the concept. With titrations, we've got a nasty that we do. We say to you, this is titrated with this, but it doesn't reach the end point. Titration equation. Poof. Can't use it. Titration equation only works at the end point. Okay. So we'll discuss that. So here is your dilution equation, which if you're a lab tech, you're going to use this. Okay. So your number of moles of solute doesn't change. So C initial, V initial equals C final, V final. They equal each other, and you can then work out what V final must be and what the volume added must be. Okay, good to know. Do you get it as a standard equation? No. You get C equals N over V. You do not get this. You do not get that. Okay, cool. If 62,5 grams of magnesium hydroxide is dissolved in 350 cubic centimeters of water, determine the concentration of the solution. So let's do this. Okay, so take the first one. Okay. Okay. So let's do this. So what are we given here? So we've got the mass of the sample is 62,5 grams. Is dissolved in 350 cubic centimeters of water. Now watch what I do here. The volume of the solvent is 350 cubic centimeters. The volume of the solvent is 350 cubic centimeters, which I divide by 1,000 to make it 0.350 cubic decimeters. But this is also equal to the volume of the final solution. All right, so we're assuming 100% dissolving. Okay, so this is important. Then, determine the concentration of the solution. So we want the concentration of the solution. So what are we missing? What are we missing? What do we need? Don't we have that concentration is mass over molar mass times volume of solution? So what do we have? We want the concentration, we have the mass, we have the volume of the solution. What don't we have? We don't have the molar mass, eh? So we say, okay, so let's work out here. The molar mass is going to be Magnesium is 24. Oxygen is 16. Hydrogen is 1 times by 2. And this is all going to be in grams per mole. So the molar mass is going to be 2 times 17 plus 24 is 58 grams per mole. So now we can pop it in and say, okay, so the concentration is the mass, which is 62,5 grams, divided by the molar mass, which is 58 grams per mole, times the volume of the solution, which is 0,350 cubic decimeters. And that's going to give us a concentration of 62.5 divided by 58 divided by 0.35, and you get a concentration of 0.377 mole per cubic decimeter cubed. Now, let's talk about notation. All right, not being a chemist, I know yes.
Did you get 3.071? Yeah.
Okay, so have I made a mistake? Let's take a look here. So we've got 62.5 grams. I could have made a mistake, it's fine. Divided by bracket 58 times 0.35. Okay, yeah. Don't know how I got that concentration. Thank you, Imra. Appreciate the audit. I rely on it. Very good, thank you. So the concentration is 3,0. We work to 3 decimal places, 79 mole per cubic decimeter cubed. Right, now there's several things I want to discuss here. We could also write this as the concentration of magnesium hydroxide, aqueous. We can write it like that. We can write it as 3,079 mole dot decimeter -3. You'll see some people put the dot between the mole and the decimeter cubed like that. Mole times decimeter cubed to the -3. Mole divided by decimeter cubed, and big M. They're all acceptable. But what happens in an exam is people do this. Mole, decimeter cubed, mole divided by decimeter to the -3. You lose a mark. Don't do that. Any questions on that? Are you okay with that? You all right? Cool? All good. Okay. Excellent. Let's look at the next one. So next one, right, to number 2. Okay. If you want to make a 0.05 molar solution, mole per cubic decimeter cube solution. So the desired concentration is 0.05 mole decimeter cubed to the per decimeter cubed. Calcium hydroxide. Okay, so calcium hydroxide, we're going to work with the molar mass of calcium hydroxide, CaOH2. Molar mass of calcium is 40. Okay. 2 times oxygen is 16, hydrogen is 1. That is going to give us 2 times 17 is 34. Plus 40 is 74. This is 74 grams per mole. Get your units right. Okay? You can also write this as grams times mole to the negative 1. Then you see people put grams divided by mole to the negative 1. That's wrong. Okay? Be unit focused. Units are very important. All right, we have 500 milliliters. So it's a volume of the solution is going to be 500 milliliters. We divide by 1,000. Okay, it's going to be 0.5 liters, which is the same as 0.5 cubic decimeters. Okay. So how much calcium hydroxide do you need? Now this is something that you need to know how to do. You need to be able to work out what the mass is that you need to dissolve in there. Yes.
So, where I'm confused, I thought they meant how much in moles, because usually they tell you, like, what is the mass.
True.
So I didn't know.
No, that's true. That's true. I mean, much can be mole or can be grams, a mass. I agree with you. So I think if it was a test, we wouldn't be able to mark you wrong if you only did moles. I agree. Okay. But what we actually should have said there, what is the mass in grams that you need? Okay. Yeah. No. You're spot on there, Tamlin. Spot on. I should have said, what's the mass in grams?
No, it's not.
No, it's unambiguous. No, it's ambiguous. Absolutely. So concentration is the mass, which is what we're looking for. All right. So what we don't have is the mass. That's actually what I was looking for. So what we do now is we say, okay, so concentration is mass over molar mass times the volume of the solution. And this is where Callum is right in a practical chemistry situation. They don't go now and go and do successive calculations. They're just like, okay, we've got this formula, boom, use it. Okay. So what we're going to do here, so if you look here carefully, this is actually really easy because you can just say mass is concentration times molar mass times volume. Voila. And you know what? They'll probably have a spreadsheet where it's just, they pop it in and boom, out it comes. Okay. All right. So if we look at the mass here, concentration is 0.05 mole per decimeter cubed. The molar mass, we said, is 74 grams per mole. And the volume is 0.5 cubic decimeters. Now, in NSC, you do not need to write the units in your substitution. But I like to, because I want to show you something. Can you see the cubic decimeter and the cubic decimeter cancel? Can you see the mole and the mole cancel? You'll end up with grams, but that's the right thing. So you know you're using the right values, the right quantities. So your mass in grams, 74 times 0.05 times 0.5 gives you 1,85 grams. And that is a very handy. So in a practical, we could ask you in a prac exam to work out what's the mass of a solvent that you need in order to get a desired standard solution. Okay. This is important. I say in an exam, prac exam, or in a theory exam, we could ask you what mass of a particular substance do you need to dissolve in a certain volume of solvent in order to get a specific standard solution. So look at what did we ask you for? We wanted the desired concentration is 0.05. Okay, this is yeah.
Okay, because so you said moles don't change, right?
Yeah. So no, but this is the desired concentration. We saying we want a 0.05 mole per cubic decimeter cube solution. How many moles of calcium hydroxide do you need? What mass of calcium hydroxide do you need to dissolve in 500 milliliters of water?
Oh, because the moles of it isn't going to change when you.
Now you're getting mixed up with dilution. The moles don't change in dilution. We are determining the number of moles we need to put in to get a particular concentration.
Okay.
This is not dilution. You see, look at the question. If you want to make a 0.05 mole solution in a 500 milliliter beaker, how much calcium hydroxide mass-wise must you put in? This is very important. This is how you make standard solutions now. Whereas in the other dilution, now this is actually a very good question, because if I have a solid substance, so my magnesium, let's say this is calcium hydroxide. Calcium hydroxide is a ionic solid. It's crystals. Okay? So the actual solute is a solid. We measure its mass, eh? To measure the mass, we dissolve it in the water to get the desired concentration. If, however, I've got a bottle of HCl of a particular concentration, and I want to now take that concentration and use that acid to get a desired standard solution of it, which has to be lower, then I use a dilution process. So if your source of your substance is in a solution, then you use dilution to get a standard solution. So what we've done is I've shown you two methods to get a standard solution. One is through dilution, and the other one is through dissolving. Right. Okay. You see, this is the next one, is that. Yes. Sure. Okay. So the next one is where we're going to use dilution. So a 0.8 molar solution of H2SO4 is poured into a 1 liter container. It takes up 1/4 of the container. So what we have initially, we have a 1 liter container. Yeah. We have a 1 liter container, okay? And we pour a 0.8 mole per cubic decimeter solution. So this is going to be concentration 1. And if it is takes up 1/4 of the 1 liter container, then the volume is 0.25 cubic decimeters cubed. That is V initial. Do you agree? Now, how much water needs to be added? What must the change in volume be to dilute the solution to 0.55? So what we want, okay, when we add here, so we are adding here, this is delta V is the volume added. Then we're going to land up with a solution. All right, where now we have that concentration 2 is 0.55, which is the desired concentration. This is the desired concentration. Okay. We do not know what V final is yet. Okay. So I'm going to use both methods. Okay, I'm going to use both methods. So method 1, we say the number of moles is the concentration times the volume of the solution. Okay, so the number of moles is going to be the concentration, which is 0.8 mole per cubic decimeter cubed, times V initial, which is 0.25 cubic decimeters. That means the number of mole is going to be 0.2 mole. Of what? Of H2SO4. This is H2SO4. Okay. So that is the number of moles of H2SO4. Now, that number of moles is now spread over a bigger volume of solution. Right, so what we find now is if we look now at the number of moles, finally, it's the number of moles initially, all right, which is 0.2 moles. So the number of moles doesn't change. The only thing that's changed is the thing we've changed physically. We changed the volume of the solution, which has also changed the concentration. But now we know that N final is C2 V final. All right, so N final is going to be 0.2 moles. All right, we've got N final, we know is 0.2 moles. All right, concentration 2 is 0.55 mole per cubic decimeter cubed, and we're looking for V final. It's dilution. All right, so we say V final is 2 divided by 0.55, and so V final is going to equal 0.2 divided by 0.55, going to give us 0.364 cubic decimeters cubed. Okay. Right, and if you do a unit analysis, you'll see this is mole, and this is mole per cubic decimeter cubed. The moles cancel, and the cubic decimeters cubed to the -3 goes upstairs. Yes, Isabella.
So you said this is the first method you're showing us. Will you ask us to work it out with a specific method?
Okay, we don't normally ask you to work out a specific method. The only way we can guide you to force you to use a specific method is if we start adding sub-questions and we scaffold it. So we say, for instance, how many moles of sulfuric acid is in the original solution? Okay. Now, how many moles will be in the final solution? Same. What will the amount of volume of water be that you have to add? That sort of thing. Then we're forcing you not to use the dilution equation. Okay. But now, in this case, it's good to understand. Okay, so we're not finished because the volume added is V final, which is 0.364 cubic decimeters, minus 0.25 cubic decimeters cubed, which was the original volume. And so the volume added, delta V, is going to be 0, and we say that minus 0.25, and we get 0.114 cubic decimeters cubed. And that is the volume of water added. Okay, now we love to ask these kind of questions, right? And where you find this is in the acids section, okay? In grade 11 and 12, our stoichem is interwoven into, it's not stoichem, you don't get a stoichem question. Like in grade 11, you get a stoichem question, okay? In grade 11, you still get a stoichem question. But in grade 12, you don't get a stoichem question. You get a stoichem question either in a chemical equilibrium question, or stoichem question in a rate of reaction question, or a stoichem question in a acids and base question. And the place where you get stoichem the most is in acids and bases and chemical equilibrium. Okay, so now if we were to use the dilution equation, that would have been much quicker. Okay, because the dilution equation, method number 2, if I'd used method number 2, I would have basically just used the dilution equation and said, okay, well, what do we know? We know that C1V1 equals C2V2. C1 was 8. V1 was 0.25. C2 is 0.055. No, 0.55, eh? Correct? 0.55. V2. Do one calculation. Okay? So it's 0.8 times 0.25 divided by 0.55, and that gives us that V2 is 0.364 cubic decimeters, and then your delta V, which is your volume added, volume of water added is going to be V2 minus V1. And that is going to be 0.364 minus 0.25 cubic decimeters, and we know that that is going to give us delta V is 0.114 cubic decimeters cubed. Much easier. Much easier. So my advice to you is, even though you understand this or should understand this, if you're given the opportunity, just use that. Yeah. Okay. Now, don't mix it up with the titration formula. Because your titration formula, which we're going to do, the titration formula looks like this. The titration equation looks like this. The number of moles of acid equals the concentration of acid divided by times by the volume of the acid, over the number of moles of base is the concentration of the base times the volume of the base. That is the titration equation. They look very similar, but they're not the same thing. They're not the same thing. All right, they look similar, but they're not the same thing. Okay. This is based on a neutralization equation, a neutralization reaction. Okay, so this week, today, and next week, we are going to do titration calculations. Okay, we're going to work with titrations. Your titration is really very, very important, because your titration is your prac exam at the end of this year. Okay.
So
So yes, Kishan, you don't need the big M. So, let's just see here. Sorry, I'm just trying to find my bearings here. Okay, that's just moles per cubic decimeter cube. So mole divided by decimeter cube times by decimeter cube will give you mole. But your mole cancels on the other side. Can you see these actually cancel? So it just gives you a volume in cubic decimeter. So if you work it out, if you do unit analysis, can you see the mole there and the mole there cancel out? It just gives you with cubic decimeters. Okay. Now, all of this stuff ties in, and I'm going to say this and I'm going to say it again. Generally speaking, okay, your toughest questions in chemistry are question 7, which is acids and bases, and question is it question 5, which is equilibrium, or is it question 6 that's equilibrium? The equilibrium. It's 6 and you get 3 organic, so it's question 2, 3, and 4. Question 2, 3, and 4. Question 2 is organic naming and structure. Question 3 is organic properties of organic substances. Question 4 is organic reactions. That can be tough. Question 5 is rates of reaction. Question 6, chemical equilibrium with Rice tables. Question 7, acids and bases. 6 and 7 on average are your toughest questions. Then it goes, then 8, 9, and 10 are quite easy. Okay, but we get to that as we move on. Okay, so let's talk about titrations. What is a titration? Okay. So let's first talk about a neutralization reaction. A neutralization reaction, okay, equals an acid plus base reaction. Okay. So fundamentally an acid has associated with it a hydronium ion. And the types of bases that we work with are alkalis that, generally speaking, have a hydroxide ion. Okay. And there is a very, very strong forward reaction, which lands up where, remember, conjugate acids and bases, our hydrogen ion gets transferred here. Our hydrogen ion gets transferred, making this H2O and making this H2O. And so what we land up with is a neutral solution. Okay. Now, it is overly simplified because depending upon what acid and what base you are using, and we will still get into this, once the water is formed, there is a salt that is in the solution, and that salt can react with the water, called hydrolysis of salts, which then takes your pH either below 7 or above 7. We're not there yet. We will do that next week. So what I want to do today I want to do calculations with titrations. Okay, so what is a titration? Okay. A titration is the process of determining the unknown concentration It's the process of determining the unknown concentration of an acid or base by neutralizing with a base or an acid with a known concentration base or acid. Okay, now titrations, if you go to university and you do any course, whether it in chemistry, whether it be in medicine, if you do biological course, you do a chemistry course, you're going to do titrations. Okay, you're going to do titrations. Because titrations don't have to be with acids and bases, because a titration is basically using some reaction to quantitatively determine an unknown concentration. We are going to work with it in the context of acid and base reactions. Okay. So titration is the process. It's a process of determining the unknown concentration of an acid or base by neutralizing with a known concentration of base or acid. Now, underlying this are neutralization reactions. Now, remember we've done the stoichiometric, we haven't done this. Remember we did the template reactions. An acid plus a base produces a salt plus water. Remember that. So if we take an acid plus a base, it produces a salt and it produces water. Okay, do you remember that? All right, so what we're going to do is, and we'll go into more detail, is you have something called a burette. And we'll still practically show you. The burette looks like this. It's got a little valve. Okay. And that little valve you can turn. This is known as a burette. Right. It's a U, not an A, huh? Okay, it's a burette. And you normally have it with a retort stand. I always used to joke, it's not so funny anymore. I used to joke that I'm autistic and my sister is artistic. Okay. But my sister, who was a fantastic artist, actually passed away at the age of 50 from lupus a few months ago. Yeah, quite a while ago, at 50. She was brilliant. She was a brilliant artist. Without getting too morbid, but I always used to joke, used to say, I'm autistic and and my sister's artistic. She's a professional artist. But yeah, I can't joke like that anymore, eh? Without being morbid. All right, but she definitely got the art genes and I didn't. Okay. Now, all right. So here we have something called a conical flask. A conical flask. Eesh. My handwriting is particularly poor. I do apologize. We have a conical flask, also known as an Erlenmeyer flask, and in my class, a coffee cup. All right, I use an Erlenmeyer as my coffee cup. Okay, so here's an Erlenmeyer. All right, so what we do is we invariably put the solution of known concentration in there. It can be an acid or a base. So if you have an acid there, then you put a base in there. If you have a base here, then you have the acid up there. Okay? So in here, we put the solution of unknown concentration.
So is titration a neutralization?
It's a neutralization, but it's a quantitative neutralization. It's a quantitative neutralization. Yeah. Means you actually you come out with a number. Yeah. Solution of a known concentration. Yeah. So qualitative would be like, do you see the universal indicator turned green? All right, so we've reached neutralization. Great, that's qualitative. But quantitative is, do you see, we actually neutralized the 0.5 molar solution of acid with 200 moles with a concentration of 0.25. That we've got numbers. That's quantities. That's quantitative. All right, so this is the setup. So what we do, and we'll still talk about this, you also inside here, you put a substance called an indicator, which helps us. It's dependent, the color is dependent on pH. All right, now today, my goal today is to do a few titration calculations. The ins and the outs of a titration, we will still look at in more detail. We'll look at it in more detail. All right. Okay. So, now let's look at an example. Okay. We work out the following. We say, okay, here's an example. Example 1. Okay. An unknown concentration of acid. Okay. And an unknown concentration of acid is titrated, let's use that word, is titrated with 250 milliliters, 0.75 molar solution of potassium hydroxide. Okay? An unknown concentration of acid is titrated with 250 mils, 0.75 KOH solution. It is determined that 150 milliliters of the unknown sulfuric acid, I should put a concentration of sulfuric acid. My apologies, I must give you the acid. Is titrated. Let me just do this properly because I am going to post these notes. Of H2SO4. It is determined that 150 moles of H2SO4 is required to reach the neutralization point. Which we also call the end point. The end point. The equivalence point. They all basically mean the same thing. Of the titration. Okay, so key things. We have an unknown concentration of H2SO4. I'm going to use red convention-wise for acid, universal indicator is red in in an acidic solution. So I'm going to say the concentration of the acid is unknown. The volume of acid required was 150 moles. So the volume of the acid was 150 milliliters. Okay, that's the acid. For the base, I'm going to use blue. 250 moles of KOH solution of a concentration of 0.75. So we say, okay, so the concentration of the base is 0.75 mole per cubic decimeter cubed. The volume of the base is 250 milliliters. Okay, now there are two ways of doing this. I'm going to do both and then we're going to end. And I'm going to give you a few to do for next week. All right, we're going to end here before 4 o'clock. Okay, and then we'll give you 2 or 3 to do, 2 or 3 to do for next week. Okay, they go quite quickly. So, if we look at method 1, right? If you look at your flask, all right, here is your Erlenmeyer flask. All right, initially in your flask, you have got that. That's in your flask.
So if something is titrated with, right, is that the thing that's being added to?
Yes, and neutralized.
So
it means added and neutralized. So what happens is what they do, Imran, good question. What happens with titration is you slowly but surely, there are calibrations on this burette. And there's a technique that you use.
I remember. What I just wanted to double check was that acid, the base is being added to the acid.
In this case, the acid is being added to the base. Apologies. Because in this case here, the base is known and the acid is unknown. You put the unknown in the burette. Because what you're going to do now is you've got a known concentration. Look at what I said here. I said solution of known concentration.
Will it always be like that?
We work with it like that. So the solution of the known concentration is here. All right. And the solution of the unknown concentration is there. So what we then do is we run it until we reach neutralization. Yes.
So this is solution of known concentration. So is that
Sorry, unknown. Sorry, that's the confusion. That's the confusion. I apologize. That should be solution of unknown concentration. My bad. Thank you. Solution of unknown concentration. Thank you. Hear me? Okay. So what, yeah, sorry about that. I apologize for that. So what happens is when you eventually, there's a whole technique to it. But you use the indicator to give you an idea color-wise when it reaches neutralization. And when you reach neutralization, you see how much of this was actually added there. Okay. So now, if you look here, when you add the acid now, you've added the volume of acid, eh? You've added the volume of acid. Right. What lands up is an overall solution like that. And for the time being, we're looking at an indicator that implies that neutralization has been reached. Are you okay with that? Okay, now. Right, so let's move here. I'm going to look at method number 1. Method one is to use full-on stoichiometry. The first thing we do is we say the following. Acid H2SO4 plus KOH is going to produce K2SO4 plus H2O. Okay. Now this is where it's key. Generally speaking, we give you the balanced chemical equation. There is the possibility that we can give you the equation and then put it in word form and say, okay, write out the balanced equation. If you look carefully here, you've got 2 potassiums there, you need 2 there. So I'm going to write a 2 there and a 1 there. All right, now this becomes important, okay? And that's going to be a 2 there. This is the side that is important with titrations. So what we do is we say, okay, if we look at the number of moles of acid, we start off with what is known. The number of moles of base is the concentration of the base times the volume of the base. We were told that the concentration is 0.75 mole per cubic decimeter cubed, and the volume of the base is 0.25 cubic decimeters cubed. We need to convert this to cubic decimeters. That gives us, if we take 0.75 times 0.25, that gives us, and I'm going to work with the full complement of decimal places, 0.1875 mole. That's the amount of moles of KOH in that solution. Okay. Now, this is where it becomes very important. You need to look at the molar ratio. The number of moles of acid to the number of moles of base is a 1 mole to 2 mole ratio. In other words, every 1 mole of H2SO4 requires 2 moles of KOH to neutralize it, which means for every 1 mole of KOH, you need half a mole of H2SO4. So we can therefore say, this implies that the number of moles of acid, okay, is 1/2 of the number of moles of base. So if the base has got 0.1875 moles, then we need half of that. 0.1875 mole divided by 2, that gives us that the number of moles of acid that we needed was 0.09375 mole. In other words, the amount of moles of acid that was required to neutralize that amount of moles of base was that. Now, that number of moles of acid comes from the fact that it was originally in a solution of a certain volume. Well, we were told what the volume of the acid is. Sorry, not the volume of the base, the volume of the acid. My bad, apologies. Number of moles of acid over volume of acid. Now, we know that the volume of acid solution was 150 moles. We were given that. In other words, in order to neutralize the base, we used 150 milliliters. This is what we measure in a titration. We measure the volume of the unknown solutions, the volume of the solution with the unknown concentration. We physically measure it. We drop it into the Erlenmeyer we drop it, the unknown, we drop by drop. There's a set method of doing it, and you repeat it, and you find averages and all of that, and you swirl. There's a technique of where you swirl, and you swirl, and then you do a rough titer, and then you do 3 accurate titers, and then you do averaging. There's a whole technique. In essence, you're working out how much volume of acid, in this case, you need to neutralize that amount of base. Now, from that, you can go, well, okay, well, in the originals, at that amount of solution, we know there had to be 0.9375 mole in order to neutralize this amount of mole of base, which was in the Erlenmeyer, divided by, well, that came in 150 moles, which is 0.15 cubic decimeters. So if you divide this by 0.15, we get that the original concentration was 0.625 mole per cubic decimeter cubed. In other words, the concentration of the H2SO4 solution was 0.625 big M. That is a titration. Now, you need to be able to do that because we sometimes force you to do it. But there's a much quicker way.
Wait, so in a titration, are you always looking for the concentration needed?
Yeah. So you physically measure off the volume, but you're always trying to work out the concentration.
Yeah, it was just a question.
Yeah.
I don't know if it's...
Okay. Now, I want to show you method number 2. Now, method number 2 works with the titration equation. This is the last thing I'm doing with you, and I'll be done by 4. Okay. So the titration equation is at equivalence point. Now, sometimes we're naughty and we send it past equivalence point. Or sometimes we don't get to equivalence point, and then you have to do proper, long-winded stoichia. But look at this. We can say that the number of moles of acid is equal to the concentration of the acid times the volume of the acid. Okay? And we know that the number of moles of base equals the concentration of the base times the volume of the base. Now, there's something really cool about this, because in mathematics, we compare by dividing. We know that in order for neutralization to take place, these two products have to be in ratio according to the balanced chemical equation. And you don't need to work out what the actual amount of moles is, because all you need is the ratio. And with this, we know it is 1:2. Look how cool this is. So we go, okay, well, in order for neutralization to take place, it needs to be a 1/2 mole ratio. That's not exactly how many moles of base and acid you have. That is the molar ratio for neutralization. And your concentration, well, what is your original concentration of acid? We don't know. But look at this. This is so cool. We were originally given these in milliliters. 150 milliliters. Concentration of the base was 0.75. Okay. 250 milliliters. Are you ready? Don't even need to do a conversion. Milliliters cancels with milliliters. Almost done. And now, ladies and gents, we just cross multiply and divide. So we can say Ca equals 1 times 0.75 times 250. And divided by 150 times by 2. We bring the 150 downstairs and multiply it by 2. We take the product of this and you multiply it by 1. And drum roll, 0.75 times 250 divided by 300, 0.625 moles per cubic decimeter cubed.
So for the titration equation, we must
Sorry, what did you ask?
for the titration equation, we can leave it. So we don't have to convert. If we do convert, we get the wrong answer.
This, you can do it just like that.
We get the wrong answer then.
Only at equivalence point. But here's the downside. You don't get the titration equation on your formula sheet.
Wait, sorry, so if you change it to decimals cubed,
It's fine. Doesn't matter. It's the ratio that's important.
will you get the same answer?
Yeah, 0.15 over 0.25 gives you the same as 150 over 250. If you divide by 1,000 on the top, you divide by 1,000 on the bottom, you're dividing by 1. Doesn't make a difference. You can have cubic decimeters, cubic meters, cubic meters. You can have cubic kiloliters, whatever. As long as the units are the same. Gives you the same ratio. Thank you very much, ladies and gentlemen. I am on time. Thank you. I will post it on the class tomorrow with homework.